Alrighty guys, so tonight we're going to be talking about equilibrium, which is talking about the rates of different reactions and how they are affected. So reaction rates are something that we use to describe every different reaction because all different reactions occur at different rates. So striking a match will cause it to almost immediately erupt in flame, whereas converting dead plants or animals into oil takes millions and millions of years. So those are just kind of two extreme examples. But reaction rates are measured as the speed of any change occurring over time. So it's all talking about what's happening over time, or what's happening to the reaction over time. And these reaction rates occur due to something called collision theory, which we've talked about in the past. I just haven't necessarily specifically called it collision theory. But we talked about it in our thermo unit, last unit, when we were talking about how reactions differ endothermic versus endothermic. And collision theory states that atoms, ions, molecules, etc. will react to form products after colliding with each other, providing that they collide with enough energy to overcome the activation energy of the reaction. So that is kind of, this collision theory is the idea that is the overriding principle for reaction rates and what's going to determine the reaction rate. It's all based on the activation energy and the number of collisions you can have. And the key thing that we're going to be thinking about here is remembering that these reactions occur and these collisions, as these collisions occur, and we've talked about this in terms of exothermic reactions, as collisions occur, not all collisions are going to have enough activation energy to overcome, or have enough energy to overcome the activation energy. Sometimes they do. If they collide with enough energy, they will overcome the activation energy. The more collisions you can have, the more likely you are to have collisions that have enough energy. So essentially you kind of want to increase, if you want to increase the rate of a reaction, you want to increase the number of collisions that are occurring. And we can do that through a variety of ways. So there are different factors that will affect reaction rates because reactions occur at their own rate, some fast and some slow. And varying conditions of a reaction can actually modify the reaction rate, but only certain conditions that change will actually affect reaction rate. But these factors can affect that rate. Temperature, concentration of both reactants and products, particle size, and use of catalyst. And so we're going to be talking about these 4 different factors affecting reaction rate for a minute. So temperature, as you increase the temperature, the particles begin to move faster. This means that they collide more frequently, which means that more collisions will occur which have enough energy to overcome the activation energy, increasing the rate of the reaction. The exact effect depends on if it's an endothermic or an exothermic reaction, but a good example of an exothermic reaction is if you strike a match and light a coal on fire, or ignite a coal, it will start reacting to produce carbon dioxide and oxygen. Now, in doing that, once you kind of get it started by increasing the temperature of it, then the energy that is produced through the reaction of those coals and making it into carbon dioxide and water, that energy that you just produced is going to be enough energy to help increase the energy of the system, meaning that as those collisions are now occurring, they're going to occur, more and more of them are going to occur with the correct energy to overcome the activation energy and actually cause the reaction to go. Concentration, it's kind of similar. Increasing the concentration of a reactant increases the number of particles that are present. When you increase the number of particles, that means that they're going to collide with, you're going to have a greater frequency of collision, which means that more collisions are going to occur which have enough energy to overcome the activation energy, and therefore increases the rate of the reaction. So we kind of did this in the micromole rocket lab when we had our pipettes, and when we were looking at the ratio, if we had too much hydrogen versus oxygen, we made a small pop, but when it was all oxygen, it made that really big pop. We increased the amount of oxygen available to undergo combustion, and therefore we had a bigger pop because we had more reactant to increase the rate of our reaction. So more collisions that were occurring, we're able to actually go. So let's next talk about particle size. So decreasing the particle size actually increases the surface area, and it's the surface area of a particle where the reaction occurs. So by decreasing the particle size or grinding it up into smaller and smaller pieces, that increases the amount of surface area you have available to react. Increasing that surface area means that you're going to have more reactant available to react, increasing the number of collisions or the frequency of collisions, therefore increasing the reaction rate. So you can kind of think about it if you think about ice. This is kind of like a example that you might be able to understand. If you have ice in a glass, like a big cube of ice versus a bunch of small crushed ice pieces, if you look at like the amount of time it takes for that ice to melt, the cubed ice, because it's so much bigger and it doesn't have a lot of surface area, is going to take more time to melt than the crushed ice, which now has a bunch of different surface area, and so it's able to melt faster because it's got more surface area for that's being heated up and causing it to melt. And then the last one is the use of a catalyst. So catalysts are specifically designed to increase the rate of a reaction by providing an alternate pathway for the reaction to take place with a lower activation energy. The cool thing about catalysts is that they're not actually used up in the reaction, and they don't really participate in the reaction. We've used catalysts before. Let's see. Manganese was a catalyst in the micromole rocket lab in the decomposition of hydrogen peroxide into hydrogen gas and oxygen gas, or into hydrogen gas, and what was the other one? It wasn't oxygen gas, it was hydrogen gas and I think water. But the manganese actually wasn't participating in the reaction. You weren't making manganese oxide or anything like that. No, it was oxygen gas and water, sorry. The manganese wasn't participating. You weren't making manganese oxide or anything like that. The manganese stayed exactly as it was, and it wasn't used up in the reaction. It was just acting as a catalyst. Sometimes heat can be considered a catalyst, or sometimes actual physical substances like manganese or zinc or platinum are used as catalysts. And so what catalysts do, you can kind of see here. Here, this black line is my reaction, going from reactants to products. And I've got this dark blue activation energy. It's pretty big. And I've got this dark red delta H. Now, this activation energy might cause the reaction to be kind of slow. And so if we provide a catalyst with a lower activation energy requirement, this light blue, we can actually make the reaction happen faster, because if you've got a lower activation energy, you don't require as high energy of collisions, meaning that since you're not requiring as much high energy, more reactions that are occurring, or more collisions that are occurring, are going to have enough energy to overcome this smaller activation energy. So it's not that you're increasing the energy of the system, you're just saying, okay, so let's say only 10 reactions had an activation energy of 250, but 20 reactions had an activation energy of 150. Well, now we're lowering that activation energy threshold to 150, so now instead of just 10 reactions occurring from collisions, 20 are going to. And so the reaction occurs faster because more collisions have the ability to actually proceed. And so you'll see that the delta H doesn't change. We're not changing the products or the reactants at all. We're just changing the requirement for that activation energy. So those are factors that can affect reaction rates. And now we're going to talk about equilibrium and the whole idea behind that. So in the past, we've pretty much said that reactions occur in a forward direction. However, not all reactions are one directional. Many reactions will actually occur in both directions. That means that they're reversible, meaning that both a forward and reverse reaction are occurring. So you have both of these occurring at this, sometimes at the same time, sometimes not. It depends on, or sometimes it's more like that they're able to occur, but when we talk about a specific situation of equilibrium, they're occurring at the same time. But reactants are becoming products, or products are becoming reactants, both the forward and the reverse reaction. So an example of this is 2 sulfur dioxides plus oxygen gas making 2 sulfur trioxide gases, or 2 sulfur trioxides will decompose into 2 sulfur dioxides and oxygen. So that's an example of a reversible reaction. Now there's something called chemical equilibrium, which is kind of the big part of this unit that we're going to be talking about. And equilibrium occurs when a forward and reverse reaction begins to occur at the same rate. It's called equilibrium or dynamic equilibrium. And what this means is that at equilibrium, there's no net change in the amount of components in the system. This doesn't mean that there are equal amounts of each compound, just that the amounts are not changing. So we're no longer producing like more reactants or more products. It's occurring at the same rate, so that as we produce products, we're also producing reactants. So the overall, there's no net change. So if we write our reverse reaction, we don't write those as 2 different reactions, we write them as one single reaction. 2SO2 plus O2 making 2SO3, and it has this cool reversible arrow. It's like a half arrow going forward and a half arrow going back, because they're both occurring at the same time. And when they're at equilibrium, they're occurring at the same rate. So what that kind of looks like here, this graph on the left is showing the forward reaction, where you can see that we start out with 0 concentration of SO3, but that builds in over time and eventually levels off. And in the forward reaction, we start out with lots of SO2 and O2, which as we're producing SO3 starts to decline. On the reverse side of that, we start out with a lot of SO3, which slowly decreases because we're producing reactant, and we start out with 0 reactants, SO2 and O2, and we slowly produce those as we are going backwards. Now you'll notice that eventually they level off, and this is actually the same level because we've produced the same amount of sulfur dioxide and oxygen as we have sulfur trioxide. And so these reactions are occurring at the same rate. It's kind of like that idea of vapor pressure, that if one molecule of liquid becomes gas, one molecule of gas has to become liquid. That was called the dynamic equilibrium of vapor pressure. This is the dynamic equilibrium of any reaction. As the reactants become product, the product becomes reactant, and it happens in such a way that they're not changing. They are occurring at the same time. So I've got kind of a fun example of what that looks like, or what you can think of that, because sometimes it's hard to visualize it like that. So key thing is that in dynamic equilibrium, the reaction does not stop. The forward reactions and reverse reactions are just now occurring at the same rate. So here I've got two escalators. On the bottom side, you can consider these are reactants and these are products. You'll note that the forward reaction is going from reactants to products, the reverse reaction is going from products to reactants. This is in a state of equilibrium, or dynamic equilibrium, because I have 4 people going up and 4 people coming down. So if one person got off, one person would get down here. Okay, so it's the same number of people going up as they are going down. That's equal. The rate of the forward and reverse reactions are equal. The thing that's not equal is our number of reactants and products. I have 4 reactants down here and 5 products up here. It doesn't matter that I have more or less products or reactants. Those don't have to be equal. The only thing that has to be equal is my rate of reaction, the number of reactants becoming products and products becoming reactants. That is what it means to be at equilibrium. Now, because we talk about equilibrium, and it's kind of a cool thing, we like to have a way to discuss it. And so we talk about it in terms of something called the equilibrium constants. And this is a way for scientists to express the position of the equilibrium. And we call it the equilibrium constant, or KEQ. And it's about the ratio of the product concentrations to reactant concentrations. So if I have a reaction of AA plus BB going to DD plus EE, where lowercase a is talking about the moles and uppercase A is talking about the compound, the equilibrium constant is the concentration of products raised to their moles, or their coefficients, that's the word I'm looking for, over the concentration of the reactants raised to their moles. So it's the concentration of D raised to D times the concentration of E raised to E over the concentration of A raised to A and B times the concentration of B raised to B. So this is going to make more sense when we actually do an example, but I wanted to kind of show you the idea of an equilibrium constant. The cool thing about equilibrium constants is that we do not include solids or pure liquids because those are not considered part of the equilibrium constant expression. And they have no units, so no half points off on a test because you forgot your units, because there are no units. So the concentrations that you've got there all cancel each other out, leaving you with no units at the end. Now, equilibrium constants are not affected by really anything except for temperature. Heat is the only factor, temperature is the only factor that will affect equilibrium constants. But it affects endo and exothermic differently. For an endothermic reaction, adding heat causes the equilibrium constant to increase, whereas removing heat causes it to decrease. And for an exothermic reaction, adding heat causes the equilibrium to decrease, and removing it causes it to increase. So this is something that we're going to be talking a little bit more about when we talk about shifts in equilibrium, but I wanted you to know that, and I'm going to give you this fancy little table here that just puts everything that we have on the left there into a nice little table. This is going to make a little bit more sense when we talk about shifts in equilibrium, because this is really related to that. So I will talk more about this later, but I just wanted to give you a brief intro. So I know that that was fast and it was a lot, but we are going to talk about it in class tomorrow. Please come prepared with some notes and some ideas so that when I ask you what's going on, you can tell me and you don't just stare at me, because it's about you teaching me, not me teaching you. So you've got the front load. Now you can carry on and teach me tomorrow. All right, guys, see you later.